Hey guys, Mr. Backward here. In this video, we're going to look at Newton's method. So Newton's method is a numerical technique for approximating a zero of a function with zeros of its linearization. Under favorable circumstances, the zeros of the linearization converge rapidly or rapidly approach an accurate approximation. Many calculators use this method because it applies to a wide range of functions and usually gets results in just a few steps. So here's how it's going to work. To find a solution of an equation f of x equals 0, we begin with an initial estimate, which we're going to call x sub 1, found either by looking at a graph or by simply making a guess. Then what we're going to do is use the tangent to the curve y equals f of x at x1 comma f of x1, so the point created by that x1 value that we choose in our original function. And then we're going to approximate the curve there. Then the point where that tangent line crosses through the x-axis is going to be our next approximation, which we're going to call x2. Now that x2 value is usually a better approximation to the solution than your x1 guess is. And then the point where the tangent to the curve x2 comma f of x2 crosses through the x-axis is going to create our next approximation, which is going to be x3. And again, x3 is going to be a better approximation than x2. And we're going to continue this process using each approximation to then generate our next approximation. And we're going to keep doing that until we get close enough to our zero to stop. So visually what's happening here, we're looking at this blue curve. That's our y equals f of x function. And we're looking for this 0. And what we're going to do is pick some x1 value. And then we're going to find our tangent line at the point created by our x1 guess. And then what we're going to look for is where that tangent line hits the x-axis. That gives us our x2 value. So then we find our tangent line at that x2 point. And again, we look for where that hits the x-axis. Find the tangent line at that x3 value. Then as we keep doing this, these x values that we're coming up with keep getting closer and closer to the 0 of the function that we're trying to find. So here's how the procedure for Newton's method is going to work. First thing we're going to do is guess a first approximation value to the solution of the equation f of x equals 0. And we might want to pull that value from the graph so we could graph the function out and look for approximately where we think the 0 is happening. And then what we want to do is we're going to use that approximation to get a second approximation, the second approximation to get a third approximation, and so on and so on. And here's the formula that we're going to use. This says to get the next x value approximation, what we're going to do is take our previous approximation minus the function at that previous approximation value divided by the derivative of the function at that previous approximation value. So in this example, we're going to use Newton's method and that formula that we just looked at to help us solve the equation x cubed plus 3x plus 1 equals 0. So let me write out that Newton's formula again. So it was x sub n plus 1, and that just means your next approximation value. What we're going to do there is take the previous approximation guess minus our function value at whatever number we're guessing over the derivative of that function at whatever number we're guessing. And we can use this formula however many times we need to in order to come up with a good approximation for what our 0 is going to be. Now we're going to need the derivative for the bottom of this fraction, so let's do that right away. So I'm going to drop the 3 down, so this becomes 3x squared. The second term will be plus 3, and that 1 is going to derive into 0, so we don't really need that. So this is the derivative of our function that we're looking at. Now what I'm going to do is actually graph out this original function so that I can approximate a 0, and that's what I'm going to use in here as my first x sub n value. And what I'm actually going to do is I'm going to take this Newton's method and I'm going to type that into my calculator, and I'm going to store key whatever my guess is and then let my calculator do most of the work for me. So what we're going to do is in our calculator, we're going to type out this Newton's method. And the way we're going to type it out is x minus our f of x function, so the x cubed plus 3x plus 1, all being divided by that 3x squared plus 3. And then what we'll do, like I said, is we're going to store key our guesses, and then we'll let our calculator do all the work using that equation that we've got typed in. So in my y equals screen on my calculator, I've got that equation typed in. I'm going to do zoom 6 to get my standard viewing window. We're trying to approximate where we think this 0 is happening. Now it's on the negative side, and it looks like it's a little bit less than negative a half. So maybe like negative 0.25 as our first guess. So I'm going to go back to my normal screen here. I'm going to take negative 0.25 and store that as my x value. But then what I need to do is type out that formula for Newton's method. And we said we were going to do x minus, now I'm going to make a fraction. On top of the fraction goes the original function. So that was x cubed plus 3x plus 1. On the bottom goes the derivative of that function. So that's 3x squared plus 3. And then what's going to happen is it's going to take that guess that we've got and plug it in for the x in there. That answer that we get is going to be our second approximation value. So then what I'm going to do is store key that answer as my new x value, and then I'm going to rerun that formula for Newton's method, and it's going to give me my third approximation value. And then what I'm going to do is store key that as my x value. And then I'm going to run that formula again for Newton's method. So this is my next approximation value. Now, if we take a look at these approximation values, this one that we just got isn't that much different than our previous one, but it is slightly different. So what I'm going to do is I'm actually going to keep doing this until there is no change in that answer that we get. So I'm going to take that previous answer, store it as my x, and then again run that Newton's method formula again. And then I'll compare it to our previous answer that we got earlier. And what I notice this time is that these values are exactly the same. So what's happening in here? Your calculator can only display so many decimals for your answer. And after we get to this point where it's just giving us the same answer every single time, we're never going to notice any other changes in what that 0 is going to be using this approximation method on our calculator. So we can say, going to 10 decimals worth of approximation, that the 0 is happening at about negative 0.32218535546. Now there are some times when Newton's method might not work. One case where Newton's method won't work is if the derivative of our function at that first x value that we're checking is equal to 0. So if there's a flat horizontal tangent line there. So in that case, we would just want to pick a new starting point. Now there are also times where Newton's method doesn't converge on a specific x value. So if we were looking at this function f of x in here and we're looking at this r value in the middle, the values we're testing might bounce back and forth between this x1 and this x2, so we never really get any closer to whatever that r value 0 is. And then sometimes, depending on your function, you might actually converge to a 0 that's not the one that you were expecting. And sometimes that can happen if the starting x value that you choose isn't close enough to the 0 that you're looking for. So as we're looking at this picture, we want to find this 0 on the right-hand side of our picture. And so we're testing this x1, but as we test that, we actually get closer and closer to the 0 on the left-hand side. So we found a 0, just not necessarily the one that we were looking for. And if that's the case, then we would just want to pick a starting point that's closer to the 0 that we're looking for. That's going to be it for this video. Thanks for watching.